Now, in the last section, I pulled a little fast one. I introduced the concept of the moment of inertia without actually doing any calculations. And again, moment of inertia is very important because it tells us, well, essentially how difficult it is to change a rotating object's motion. Very similar to mass, which is a measure of translational inertia, in that by Newton's second law, the more mass something has, the more force we need to change the object's momentum. So calculating the moment of inertia means we need to not only take into consideration what the mass is, but where the mass is located. The moment of inertia is basically the product of the mass times the distance from the axis of rotation. So what affects the moment of inertia? Well, first of all, mass. The more mass you have, the more moment of inertia you're going to have. But also, how that mass is distributed for a certain axis of rotation. You will have different moments of inertia for different axes of rotation. Most of the time, we use the axis, which reflects the symmetry of the object, but we can also calculate the moment of inertia for more unusual axes where an object wouldn't necessarily be expected to rotate about. But again, there's a major difference between the moment of inertia and the mass, okay? The moment of inertia depends on how much mass and how far it is from the axis of rotation for a rigid body. Let's do a very simple calculation. Let's say we have 3 masses here, and I want to know how this whole system is going to rotate about the y-axis, okay? How that moment of inertia is going to be with respect to this. Now, the first thing I notice is this center of mass is not the origin of this axis. So if I were to rotate this thing, it would create a vibration due to the fact that it's not rotating about its center of axis, okay? In fact, wheels are balanced only when we've minimized their moment of inertia, okay? Rotating objects like to rotate around the axis, which has the lowest moment of inertia, because if I move that axis a little bit away, it's going to result in you know, an unbalanced situation, if you will, and we'll see later on why that's so. Now, again, each of these bodies are going to contribute to the moment of inertia. Well, in fact, this isn't, because that's right at the axis of rotation, so that has no contribution. But the mass here times its distance squared, r squared, r is 1/2 a meter here. The mass here times its distance squared. I put them into this equation here, and notice that even though this is a negative value, when it's squared, I still get a positive value out of it. So the total moment of inertia for this is the moment of inertia of each object, which is 1.25 for this. It's 0 for the center one because r is 0. And it is 4 for this one, gives me a moment of inertia of 4.25 kilograms meter second. I want to say meters per second, but it's meters squared, meters squared. Again, given the 3 different masses at 3 different locations, I get a contribution from each. What about a more complicated system? Here's a set of masses that we actually calculate the center of mass for. So when I try to rotate this will actually be unbalanced. But let me calculate the moment of inertia for the y-axis and the moment of inertia for rotating this about the x-axis. Again, I can have multiple moments of inertia for this particular system. So I go ahead and do this. I do it for the y-axis, which is actually my x distances squared. Notice that my y-axis, if I rotate on this axis, I'm concerned with how far these masses are from that axis that I'm rotating on. And for the x-axis, rotating this way, I'm concerned about how far the masses are here. So these 2 masses contribute to the y-axis moment of inertia. Only this mass will contribute to the x one. I make calculations simple for myself. So here we go. 5 times -2 squared, that is this mass right here. 4 times 1 squared, okay? And then again, I get 16 kilograms meters squared. For this one, I have 5 meters at 2 meters. I'm sorry, 5 kilograms at 2 meters. I square the 2 meters, that's 4 times 5, that's 20. The other two are on the axis, so they don't contribute. So again, here we have 2 degrees of freedom by which this can rotate. And in both cases, I get a different moment of inertia. So in fact, this is easier to rotate about the y-axis than it is about the x-axis. In fact, the easiest place to rotate it about would be around its center of mass. What about a long bar like this? I'm going to do 2 different moments of inertia for this. I'm going to do a moment of inertia for the center of it, and then I'm going to extend that to the idea of a moment of inertia if it were rotating around the end. Okay, so what we do here is we integrate our dm for each r squared. Okay, in this case, r squared is in the z direction, so I'm going to integrate from -L down here to L in the z direction. So r squared becomes z squared, okay? Rho represents a linear mass density, how much mass we have per unit length. And that's just a constant, goes out front. And here's my integral, z squared integrated becomes z to the third. I go from -L to L, okay? So that becomes L cubed over 3 minus -L cubed over 3. That just becomes 2L cubed over 3, okay? Now my density is the mass divided by the overall length. This went from -L to L, so it was 2L long, the mass per length, 2L. The 2's cancel out. L cubed divided by L becomes L squared. I get 1/3 ml squared for this. And again, that's for a bar which goes from 0 to L, 0 to L, okay? So the total length is twice this L. If I take L squared, okay, and substitute that into here, that L squared actually becomes capital L over 4. 4 times 3 is 1/12, and I get 1/12 m total length squared. Now, if I were just to rotate about the end, okay, just cut the other end off, I would get 1/3 ml squared for my moment of inertia. And you can see that 1/3 is much larger than 1/12. But it's obviously easier to rotate this bar around its center right there. Okay, let's go to something more complicated. Let's go to a ring. All right. I said more complicated is actually easier. What is a ring? A ring of mass is really just a mass of constant radius. So I'm going to integrate this again. I'm going to integrate r squared dm. R is a constant, so r squared just becomes a constant out front. The integral of dm means just add up all the different masses. If I integrate dm, I just get m. That's really simple. A ring of mass is just mr squared, okay? And we saw that when we looked at the hollow cylinder rotating down the inclined plane. A hollow cylinder is nothing but an extruded ring in 3D. And again, the same argument holds. If the radius is all constant, I can take this r, pull it out in front. I'm just integrating over the total mass of the cylinder, okay? Just m, I still get mr squared. Okay. As we get to more complicated bodies, the math is not as simple. Now we're going to go to a solid cylinder. I can do this one of 2 ways. I can approach it from doing different rings of various diameters, or I can do it from the approach of, let me do my polar coordinates and just do it in 3 dimensions. That's what I'm going to do. I'm going to get the exact same result in both cases. So I equals r squared dm. We're going to say here that instead of using a linear density like we did for the ring, whereas mass divided by length, we have mass divided by volume. The volume of a cylinder is pi r squared L, so that's what this density represents. So every little infinitesimal piece of mass equals the density, okay, times the volume. You should know that dV for polar coordinates is r dr d theta dz. I know they use rho, but I've used rho for density, so I'm going to use r here. So I'm going to integrate this, okay, dm, again, r squared dm. So dm is replaced by this long set of variables, okay? R squared is still r squared. And again, the density can come out front because that's just a constant. So I have r squared times r is r to the cube. I'll integrate in the radial direction. The integral of r cubed is r to the fourth over 4. I'll integrate along the z-axis, which is the 0 to L, the length of this cylinder. Okay, that just gives me L, right? The integral of dz is just z. Okay, z minus 0 is, I'm sorry, L minus 0 is just L. And then I'm going to integrate, around the theta direction from 0 to 2 pi, which just gives me 2 pi. So rho 2 pi times L, those are the first elements, times this integral, which is r cubed over 4. Okay, the 0 is just 0 there. Now I'm going to say, I'm going to replace rho with m over pi r squared L. That's this right here. That's my rho. Pi cancels out with pi. R to the fourth divided by r squared is just r squared. M, okay, remains. L divided by L cancels out. And we're left with 1/2 mr squared. Seems like a lot for this. We could have also just calculated the moment of inertia for a disk and then just extended it in the z direction. We would have gotten the same result, probably with a lot less fuss. Yeah, essentially the math wouldn't have been any more difficult. But again, using rings or using disks, we pretty much would get the same result. Okay, what about a solid sphere? Here it's a little more challenging to do the solid sphere because this r is now going to be replaced by this equation right here. R squared equals the radius of the whole sphere, okay? But the radius of each disk, okay, is 0 down here and is maximum at the equator. So what describes that type of situation? Okay, this is actually, if we think about this in cylindrical coordinates, r would be sort of like our z function, and r is x squared plus y squared. If you do enough of these integrals, you recognize that it is the total radius minus z squared. But I'm going to replace this right here, where this sits right here. I'm sorry, where this sits right here. And, basically, let's go through each step. Here's my original integral, r squared. Here's my dm. dm is going to be the density times the volume. The volume is the area of each circle times infinitesimal width, dz, okay? And then that just becomes rho. The area of the circle is pi r squared, dz. So this is going to go in for dm. That's going to go in right there. So that's our rho pi r squared dz. And then our r squared just remains r squared. We combine these, take out our constants out front, okay? Now I'm going to replace r to the fourth with r squared squared, okay, which is r squared minus z squared, then squared. I do this integral, I get this integral right here. Remember, it's not just r squared minus z squared. That'd be simple. That'd be easier. I get this more complicated integral, and then simply integrating from negative r, which is the bottom of the sphere, to the top of the sphere, which is r. We're integrating here in the z direction. I know it's a sphere, but we're actually using polar coordinates here. Okay, we're going the z direction here. I get, this, which simplifies to 2/5 mr squared. Okay, So that's where we saw our solid sphere had a moment of inertia less than the disk. Now let's bring this to the hollow sphere. This is actually going to be easier than this one right here. I'll replace my disks with rings, okay? Now I'm going to say that the total moment of inertia is going to be equal to the moment of inertia of each infinitesimal ring. Basically, we're just doing a hollow sphere now, where the rings can be varied to create the sphere around this and build that way. Di, the infinitesimal moment of inertia for each ring, is 1/2 dm r squared. We've already done the ring, so we know what that moment of inertia is going to be. It's 1/2 mr squared. So I'm just replacing that with infinitesimal values here. dm is equal to the density times dz, where the density is, again, linear density. It's the linear density of the ring. It's the mass divided by 2 pi r for each individual ring. And that's how we get that value there. Okay, so again, as I go through this, I guess, I guess we can do it that way. I got to be a little bit careful with how I did this. This is a little bit of hand waving. So we're going to go from negative r to r in the z direction, 1/2 rho dz, rho squared. Rho comes out in front. I integrate r squared. But of course, that's capital R squared minus z squared. That gives me 2 elements to the integral. I'm sorry, the integral of r squared becomes r squared z. The integral of z squared becomes z cubed over 3. So I have r cubed minus r cubed over 3. The factor of 2 comes from the fact that I'm going from the bottom to the top. Okay, so my r squared z, or r squared r minus negative r squared r, gives me 2, for this first term. I get 2 for the second term. I just pull it out front. So I have 1 minus 1/3 r cubed. That gives me 2 r cubed over 3, or 2/3. 1 minus 1/3 is 2/3. Okay, now I got a lot canceling out here. 2 pi cancels out with 2 pi. R cubed divided by r gives me r squared. Okay, and I'm left with 2/3 mr squared for the hollow sphere. Okay, and again, this was a little bit sketchy, jumping from here to here, because this density is more like a linear density than anything else. So again, different objects shaped differently will have different moments of inertia. All the moments of inertia here are for the the axis of symmetry here. Obviously, if I rotated it along an axis like this for each of these, for the cylinders, the spheres are symmetrical around all those axes. I would get a different moment of inertia, and I'd have to calculate that using integrals again for the different directions. But again, the ring or the hollow cylinder has the maximum amount of its moment of inertia because all of its mass is distributed at this maximum distance r. The hollow sphere is sort of intermediate. All the mass is distributed on the end of the sphere, but putting the axis through, there's some mass in the center and there's some mass on the outside. For the solid cylinder, you have mass distributed from the center to the outside, so it's going to be less than this. Okay, obviously, if I had a cylinder, okay, that was measured, that was made out of the same material, let's say it was made out of brass, this would weigh more than this. But here we're looking at in terms of comparable masses. If they're both 1 kilogram, this would have a larger moment of inertia. And again, here's a solid sphere. That was a pretty fun integral to do. And depending on how you rotate this, if you rotate this from the axis right here, where L is the distance from top to bottom, I get 1/12 ml squared. If I just call L the distance from the center to this n, small l, then it'd be 1/3 ml squared. And of course, if I rotate it from its n, that bar is equal to 1/3 ml squared. So again, these are just different ways of calculating the moment of inertia. This is how we came about. Some of the techniques that we used, you don't run into until Calc 2 or Calc 3. So, this is sort of an extra bonus if you have taken Calc 3. But being that this is a Physics 1 course, not all students have come across that yet. But again, moment of inertia depends not only the mass of the object, but also depends on the shape of the object. And we're going to use moment of inertia wherever we used mass before. In Newton's second law, F equals ma, it's going to become torque is equal to the moment of inertia times alpha. In momentum, we said momentum is equal to mass times velocity. Here it's going to become moment of inertia times the angular velocity is going to become our moment of inertia in the rotational direction, what we call angular momentum. Okay, so all of these different things is moment of inertia. Kinetic energy, rotational is 1/2 I omega squared. We have to know what the moment of inertia is because we need to know not only what the mass of the object is, but how that mass is distributed.